Let's prove something about graph coloring. The claim will be that the complete graph on n vertices requires n colors to be validly colored. Remember that Kn is the graph where every two vertices are connected and it has, Kn has n vertices. Okay, so the claim is that Kn requires n colors to be validly colored. And also, it's easy, if you have a graph with n vertices, you can always color it with n colors because you can just give every vertex a different color. And of course the graph will be validly covered. Every vertex has a different color, so there's no way that two adjacent vertices could have the same color. They all have different colors. Proof will be by contradiction. So let's assume that Kn is colorable by, say, n-1 colors. Well, there are n vertices. Okay, so the proof is by contradiction. We'll assume that Kn is colorable by n-1 colors. And we're trying to prove that it requires n colors, so this is a proof by contradiction. We're assuming the opposite of what we want to prove. So it's colorable by n-1 colors. That means, and remember, there are n vertices in Kn, but we're only using n-1 colors. This implies that there are two vertices with the same color, right? If we're only using n-1 colors and our graph has n vertices, it must be the case that there are two vertices that have the same color. So, but these two vertices are connected by the definition of Kn. So this implies that this coloring is not valid. And that contradicts that we had assumed that Kn was colorable by n-1 colors. So again, let me do the proof one more time. So it's by way of contradiction, we assume that Kn is colorable by n-1 colors. Remember, there are n vertices in Kn. If we use this coloring, it means that there are two vertices with the same color. But these two vertices with the same color, they're connected. By the definition of Kn, every two vertices are connected. And therefore, we've found two vertices with the same color that are connected, so the coloring can't be valid. That's a contradiction. Therefore, Kn always requires n colors to be validly colored. Just to illustrate this, notice, for example, that if we're given a graph that looks like this, this graph, well, first of all, there's a vertex with very high degree, with degree 1, 2, 3, 4, 5, 6, 7, and it's called the star graph because you have one vertex and it's radiating out all of its edges to other vertices. But this graph, even though it has a vertex of very high degree, it's easy to color. I can color all of the outer vertices green, and I can color the inner vertex red. So this graph, in fact, is too colorable. On the other hand, if you had a graph, let's see, this says 1, 2, 3, 4, 5, sorry, 1, 2, 3, 4, 5, 6, 7, 8 vertices. So 8 vertices. If you looked at K8, which I'm not going to draw, there are too many edges, but if each pair of these vertices were connected by an edge, we just proved that you would need, K8 needs 8 colors. Okay, so this graph, even though its degree is very high, there's a vertex of very high degree, it only needs 2 colors. K8 is a graph also with high degree, and it needs 8 colors. So be careful. Just because a graph has a vertex with high degree doesn't mean that it necessarily needs many colors to be colored. And we'll address this issue even more in the next video.